Let's see an example of acceptance rejection method. And this example pertains to drawing samples from the beta distribution with parameters A and B. Let's consider a random variable x that follows the beta AB distribution, where A and B are positive integers. Then the probability density function of x, fx, is given by this formula over here. We have gamma of a plus b divided by gamma a times gamma b times x to the a minus 1 power and 1 minus x to the b minus 1 power. Remember that whenever we give the distribution of a random variable, we have to also specify its support. In this case, the random variable x takes values between 0 and 1. The beta distribution is really useful for modeling proportions. For example, so something between 0 and 1. For example, what is the probability that something happens? And we know that p should lie between 0 and 1. Here, the gamma function for integers is equal to the integer minus 1 factorial. For a particular integer m, gamma m is equal to m minus 1 factorial. So let's try to use acceptance rejection sampling to draw approximately 1,000 samples from the beta 2 distribution. In other words, A equals 2 and B also equals 2. As a first step, let's try to find a proposal distribution. Let's recall that we wanted proposal distribution to wanted support to at least contain the support of the original distribution. The support for x on the beta distribution is between 0 and 1. So a natural choice for the proposal distribution will be the uniform 0-1 distribution. So let's choose the proposal distribution y to be uniform 0-1. So we know that for uniform 0-1 distribution, the PDF G is equal to 1 for all possible y's between 0 and 1. And you can note that here, x and y have the same support. So y is also between 0 and 1. In this case, let's subsequently find what is the PDF for x. We know that x follows the beta 2 distribution. So fx is going to be equal to gamma of 2 plus 2 divided by gamma 2 squared times x to the 2 minus 1 power, and 1 minus x to the 2 minus 1 power as well. And this is equal to 3 factorial divided by 1 factorial squared times x times 1 minus x. And this is equal to 6x times 1 minus x. Sorry, there's a typo over here. There should be an x here. So now we have fx, which is equal to 6s times 1 minus x. Then we can see that the maximum value of ft over gt for t between 0 and 1 will be obtained at x or t equals 0.5. We know that gt is equal to 1 everywhere, and ft is equal to this thing. And we can see that its maximum can be obtained at x equal to 0.5. Then in this case, the maximum value of this ratio will be ft, so t we plug in 0.5, so it's going to be 6 times 0.5 times 1 minus 0.5 divided by gt, which is equal to 1, and that equals 2/3. Recall that when we choose the proposal distribution, we also want to choose a c value so that the inequality of ft over gt less than or equal to c is satisfied. In this case, let's choose c equals 2/3. Recall that we want the c value to be as small as possible for that inequality to hold. So C equals 2/3 is the smallest C value we can choose, such that this inequality ft over gt less than or equal to C still holds. Okay, so let's now try to obtain the sample inside R. Note that in step 1, we have already chosen a proposal distribution and have specified a C value of 2/3. So in step 2, let's draw the samples of the y's from the proposal distribution. But how many samples should we draw if we want about 1,000 samples of x? Should we draw 1,000 y's? Probably not, because we know that some of the y's will get rejected and we cannot use those samples. Note that in this case, when C is equal to 2/3, our theoretical acceptance rate for the procedures will be the reciprocal, which is equal to 2/3. Therefore, to draw approximately 1,000 accepted samples of x, we probably need to draw about 1,500 samples of y, because 1/3 of them will get rejected approximately. This is implemented by y is equal to our unif 1500. So this is drawing from the proposal distribution y. The y's will be the samples we get in step 2, which is from the proposal distribution. In step 3, recall that we want to draw uniform random variables for doing the acceptance rejection test in step 4. So in step 3, we draw 1500 u's from the uniform 0, 1 distribution. So we have another random vector u, which is also equal to our unif 1500. You should note that here, although both u, which is given by our unif 1500, and y, which is sampled from the uniform 0, 1, are from the uniform 0, 1 distribution, they have different meanings over here. The u's here are drawn in step 3, explicitly always from the uniform distribution. And the y's here were drawn from the proposal distribution. We chose the proposal distribution to be the uniform distribution. However, in general, the proposal distribution doesn't have to be the uniform distribution. Okay, so we have drawn our proposal random variables and the use. Let's implement step 4, the acceptance or the rejection. Let's now test if for each I between 1 and 1,500, this inequality is satisfied. There's another typo over here, but for continuous variables, it shouldn't matter too much. This should be less than, to be consistent with the lecture slides earlier. Okay, so first we supply in the R code the C value, and we know that it's equal to 2/3. Now we're going to create a logical vector of accept or reject. In other words, this vector is going to have length 1500, and it's going to be equal to true whenever the inequality test is passed and we decide to accept the sample, and is equal to false otherwise. To do this, let's say accept is assigned a value of the outcome of the inequality test of u less than ft over fy over cgy. So we know that fy is given by 6y times 1 minus y, and cgy with gy equal to 1 is just simply c times 1. So we're testing for each of the uniform draws whether this is satisfied. And then this outputs a true-false vector, which tells us whether each of the y's should be accepted or rejected. Lastly, let's toss away the rejected samples and keep the accepted samples as our draws for x. Let's call the draws for x x beta. So the draws from the beta distribution, and that's going to be the subvector of y, the draws we obtained from the proposal distribution, such that they were accepted. So let's take a look at how this worked. First, let's take a look at the acceptance rate empirically and check whether it agrees with the theoretical acceptance rate. We can do this by performing the mean function on the logical vector accept, and it tells us what is the percentage of times that accept equals true. And we can see that this is quite close to the theoretical value of 2/3, so 66.7% of the time. So it's actually very close to the theoretical value for the acceptance rate. Now let's take a look at the samples that we have drawn. Again, we want to look at the empirical versus the theoretical densities. We can first plot the empirical or the observed density of x beta, which are the accepted samples, and then we overlay the curve for the theoretical PDF of the beta distribution with a equals 2 and b equals 2. First, to create the observed histogram of the observed density, we do hist x beta. Again, frequency equals f. And then we get the histogram over here. Then we overlay the PDF for beta 2. Between the interval, so x are the possible values between 0 and 1, incremented by 0.01. In this case, we can calculate fx by using 6x times 1 minus x. That's what we derived earlier. However, let's use the built-in function for the beta distribution in R in this case. So that's called the d beta function. So again, d stands for density. So d beta gives the density of a particular x value following some sort of beta distribution. So we can do d beta xx for each of the x-axis between 0 and 1. And the shape 1 and shape 2 parameters are essentially the a's and b's. We specify them to be 2 and 2. Lastly, we include the curve by using the lines function, color equals red, and that's the theoretical PDF for the beta distribution with a and b equal to 2. We can see that again, the empirical and the theoretical density seem to agree. In other words, the accepted samples we drew in this way, the x betas, indeed seem to follow the beta 2 distribution, which is great. Let's take a look at another thing, which is the observed versus the theoretical quantiles for the random samples. So let's check the agreement between these two. First of all, we tell R what are the quantiles or the percentiles we want to look at. We say P is the sequence from 0.1 to 0.9, incrementing by 0.1. So this tells R that we want to check the 10th percentile, the 20th percentile, all the way to the 90th percentile values. First of all, let's look at the empirical or the observed quantiles. Let's call it Q hat. This can be obtained using the quantile function in R. We simply need to feed in the vector of observations we have, which is the x betas we have drawn, and the P or the percentile values that we want to look at. We can also get the theoretical quantiles for the beta distribution, and this can be obtained using the Q beta function, Q standing for quantiles. We plug in the P's again, telling R what are the percentiles we want to look at, and the parameters for the beta distribution. So A and B are both equal to 2. So let's check the agreement between these two. Here's the printed outcomes for Q hat and Q theo. We can see that they agree to a large extent, which means that looking at the theoretical and the observed quantiles, it seems that the x betas that we have drawn using acceptance rejection sampling indeed follow the beta 2 distribution.